In this video, I will show you how to use our derivative rules to evaluate limits like these, which are actually derivatives in disguise. First, we must remember the definition of derivative. Let's start with the traditional definition of f prime at c. It goes like this. The limit as h approaches 0 of f at c plus h minus f at c over h. That's the traditional definition of derivative. Next, let's do the alternate definition of derivative, which looks a lot like an old school slope. So the limit as x approaches c of f of x minus f at c divided by x minus c. So it's sort of a y minus y over x minus x limit. For problem number 1, let's set up f prime at 4 using the traditional definition of limit and the function x squared. So the traditional definition goes like this. The limit as h approaches 0. And then in the numerator, we have f at c plus h. So the function f is x squared. So this is my function f. But I need to put in c plus h. So I'm going to have c plus h squared. And then I do minus f at c. So f at c means I'm going to take the c value and plug it in. So if I take 4 and plug it in, that's 4 squared, that's 16. So f at c is 16. Then I put the h. Actually, we know that the value of c is 4. So we need to substitute that in. Now let's write an expression for f prime at 4 using the alternate definition of a limit. So we will do the limit as x approaches 4. And then we have f of x, which is just x squared, minus f at c. Again, f at c is 4 squared, which is 16. So we will just have x squared minus 16 over x minus c. So that will be x minus 4. Of course, finding derivatives by evaluating limits was the long way. And at this point in the course, we have learned our derivative rules. So if I wanted to evaluate the derivative of function f, I would just do the power rule, and I would find f prime is equal to 2x. And then if I wanted to find f prime at 4, I would just substitute 4 for x, so I would have 2 times 4, which is equal to 8. So what is the point of writing the alternate definition of derivative involving limits, or the traditional definition of derivative involving limits? Why am I putting you through this? Well, the point is that oftentimes on the AP exam, you will be given an expression like this, or you'll be given an expression like this. If you can recognize that this expression is really just the derivative of x squared, then you can do it the short way instead of trying to evaluate the limit directly. Let's set up one more derivative as a limit so we can get the feel for how it looks before we try to use the shortcut. So for problem number 2, f of x will be this expression, and the c value will be 1. So let's go ahead and set up the derivative that will give us f prime at 1. Using the traditional definition of a limit, we have the limit as h approaches 0. And then in the numerator, we have to do f at c plus h. Okay, that's what comes now. So that means I need to take c plus h and I need to plug it in here and here. Okay, so here is my function f. All right, it's something cubed plus something. So this is function f so far, but I need to do f at c plus h. So that just means I'm going to put c plus h in for both of these x's. So that's why I'm going to have c plus h here, and I'm going to have c plus h here. But then I need to do minus f at c. Well, f at c, in this case, c is 1. So I'm just going to plug in 1 for these x values. But that would be 1 cubed plus 1. 1 cubed is 1, plus 1 is equal to 2. So f at c is 2. So I'm just going to put a plus 2. And then in the bottom, we have h. Looks like I keep forgetting to plug in the c value. We know that c is 1, so it's not the final answer until we put in the 1 for c. Let's go ahead and set up the alternate definition of f prime at 1. And that is the limit as x approaches c of, now next we just have simply f of x, but in this case f of x is x to the third power plus x. Next we have minus f at c. But f at c is what you get if you plug in 1 for these x values. So you have 1 to the third power, which is 1, plus 1. So that is 2. So this is f at c. And then in the denominator, you have x minus c, which in this case will be x minus 1. I made a small mistake right here. I left this as x approaches c, but we know that c is 1. So this should be the limit as x approaches 1. Of course, the easiest way to evaluate a derivative is to use our derivative rules. The derivative of x to the third power is 3x squared, and the derivative of x is 1. To evaluate, we simply substitute 1 for x. So this is 3 times 1 squared plus 1, which is really just 3 plus 1, which equals 4. So the point of showing you these limits is that sometimes on the AP exam, they will give you a limit like this and ask you to evaluate. If you can recognize that the limit is really just the derivative of x to the third power plus x at 1, then you can evaluate it the short way like this, instead of having to actually work out the value of the limit. Same thing for this. If you can recognize that this limit is really just the derivative of this, then you can do it this way. So take a look at problem number 3. What if they gave you a limit like this on the AP exam and asked you to evaluate? Rather than trying to work out the actual limit, let's try to figure out what function this is the derivative of. So part of the key is right here. We see that we have this c plus h right here. We have a number plus h. And we remember in our traditional definition of the limit, we always start off with f at c plus h. So once you identify the c plus h, that tells you two things. That tells you that the c in this problem is 2. And it also tells you that f of x is 3 to the x power. You can see that if you took 3 to the x power and you plugged in 2 plus h, then that would give you this. What about this minus 9 on the end? According to the traditional definition of limit, in this position we should have f at c. In this case, c is 2. So f at c means plug in the 2 for x. That would be 3 squared. That would make 9. And that is exactly what you see right here. So everything checks out, meaning that this limit is really just the derivative of f of x evaluated for a value of 2. So instead of working out the actual limit, let's use our derivative rules. Speaking of derivative rules, let me remind you of one of them. If you have the function a to the x power, we have memorized that the derivative is a to the x power again times the natural log of a. So let's use that rule right now. So f prime is going to equal 3 to the x power times the natural log of 3. But for this limit, the c value was 2. That means this is the same as the derivative of f at 2. The derivative of f at 2 would be 3 squared natural log 3, which equals 9 natural log 3. So that's the answer. Let's go back and set up the alternate definition of derivative in case we ever see it written on a test as a limit. So we know that we're doing f prime at 2, and that will look like this. The limit as x approaches 2. And then in the top, we just need f of x, which is 3 to the x power. And then we need minus f at c. So if I plug in 2, that will give me 9. So that's f at c. And then we need x minus c, which will be x minus 2. So if you see this limit on a test, it's really just the derivative of 3 to the x power evaluated at 2. Let's do another one. This will be problem number 4. So we can see that we have 4 plus h inside of something. So that is going to be your c plus h. That tells you that the c value must be 4. So we know that c is equal to 4. From there, we can easily see what f of x must be, because it's whatever c plus h is plugged into. So you can see that c plus h is plugged into this negative square root. So that means negative square root of x must be the original function. Okay, what about this 2? Where's that coming from? So this should be f at c, which in this case would be f at 4. So if this is really true, if f of x is negative square root of x, then let's think about what f at 4 would be. That would be negative square root of 4, which would be negative 2. Okay, so why do I have a positive 2 here? Well, that's because in the traditional definition, you have minus f of c. So if f of c is negative 2, then you would have minus negative 2, which would be plus 2. So all of that tells us that this limit is really the derivative of function f at 4, where function f is negative square root of x. So if I saw this limit on a test, rather than trying to rationalize the numerator and work out the limit that way, it would be quicker just to use our derivative rules. So f of x is negative square root of x. Let's find the derivative of this. First, let's rewrite this a little bit. So this would be negative x to the 1/2 power. So if I want to do f prime, using the power rule, I'm just going to put this 1/2 in the front. So this would be negative 1/2 x. And then I subtract 1 from this, which will give me the negative 1/2 power. Simplifying this down a little bit, I'm going to put this x to the negative 1/2 power in the denominator, and I'm going to write it as a square root instead. So this is going to end up in the denominator. So look at my negative 1/2. In fact, let me make a little space. So I have negative. So watch this. Here's my 1/2. But this is me putting the x to the negative 1/2 power in the denominator and putting it as a square root. So we have this. So this is f prime. We decided that this limit is the same thing as f prime at 4. So I need to evaluate this at 4. So I'm going to do f prime at 4. And I'm using this form right here. So this will be negative 1/2 times the square root of 4. So that will be negative 1/2 times 2, which is negative 1/4. So this is the easiest way to evaluate this limit. Now let's set up the alternate definition of derivative in case it's ever written as that kind of a limit. So we have already decided that we are dealing with f prime at 4. But for the alternate definition of derivative, we will have the limit as x approaches 4. And then in the numerator, we have f of x, which is negative square root of x, minus f at c. So if I just plug in 4, I get negative square root of 4, which is negative 2. So that would be minus negative 2, which again will actually just be plus 2. And then in the denominator, we do x minus c, or x minus 4. So if I ever see this limit on a test, rather than rationalizing and all that kind of stuff, I will just recognize that it is the derivative of negative square root of x evaluated at 4. Let's do problem number 5. Looking at this limit, we see that on the inside of the parentheses, we have 5 plus h. So probably this is c plus h. That means everything around the 5 plus h must be f of x. So I'm guessing that f of x is x squared, because I have the 5 plus h squared, minus x, because of the 5 plus h. And I think that's it. That's going to be f of x. What about c? I'm betting the c value is the 5, because c plus h, 5 plus h, c is 5. So we have f at c plus h. To be absolutely sure that this is the derivative of f prime at c, we need to check and see where this 20 is coming from, because it should be f at c. So let's check it out. Let's do f at c, which would be f at 5, which would be 5 squared minus 5. Well, that's 25 minus 5, so that is 20. And that's exactly what we see here. So now we know that this limit is really the long way of expressing f prime at c. So if I want to find this limit, it would be quicker to use our derivative rules. Remember that f squared is equal to x squared minus x. So the derivative using the power rule will be 2x minus 1. We want to evaluate this derivative at 5. So this would just be 2 times 5 minus 1, which would be 9. So that is far easier than actually evaluating this limit. So let's write this derivative as a limit using the alternate definition of derivative, which works like this. So we want to do f prime at 5, and we're going to write the limit as x approaches c, which in this case is 5. So the limit as x approaches 5. And the way the alternate definition works is you do f of x minus f at c. So f of x is x squared minus x. So that's why I'm going to put x squared minus x right here. And then here comes f at c. Well, f at c is what you get if you take function f and plug in the c value, which is 5. If I plug in 5, I get 25 minus 5, which is 20. So that's why I'm going to put minus 20 right here. And then in the denominator, you put x minus c, which will be x minus 5. So that's it. If I see this limit, I will also know that this is really the derivative evaluated at 5 of this function f. And it will be far easier for me to evaluate it using derivative rules like this rather than trying to factor, cancel, etc. This is problem number 6, and it appears to be the alternate definition of the derivative. Remember, if it is, then this is f of x, and this is f at c. In the denominator, we would have x minus c. So if we are correct, then f of x will simply be x to the third power. C, I'll just write this over here, c would have to be 3 in this case, which means that f at c would be 3 to the third power, which would be 27. And we do have 27 for f at c. So this is definitely the derivative of this function f of x at the x value of c. So the easiest way to evaluate this would be to use our derivative rules. So f prime will equal 3x squared. And therefore f prime at 3 will be 3 times 3 squared. But that's just 3 times 9, which is 27. Now that we know f of x is x to the third power and c is 3, let's go ahead and write f prime at 3 using the traditional definition of limit, which goes like this. The limit as h approaches 0. And then remember, we have f at c plus h minus f at c. That's what's going to go in the numerator. But f at c plus h is what you get if you take c plus h and plug it in right here. So that will be 3 plus h cubed. And then minus f at c. Well, c is 3, so f at c will be 3 to the third power, which is 27. So let's just go ahead and put minus 27. And in the denominator, we simply put h for the traditional definition. So if you see this limit, you can evaluate it using the derivative rules like we did over here a minute ago. This is number 7, and it's looking like it might be the alternate definition of a limit. because we have this x minus c. So if that part is true, that means that c is equal to 1. For the alternate definition of a limit, in the numerator, we always have f of x minus f of c. I only see one term here, so it must be f of x. I will worry about the f of c later. So maybe f of x is the natural log x. Let's play around with that. So if f of x is the natural log of x, then what would f at c be? Well, if c is 1, then f at c would be the natural log of 1. But what is the natural log of 1? Remember, and I'm just going to use this as scratch paper. Natural log of 1 is the same thing as the log base e of 1. This is the power that will turn e into 1. And e to the 0 power is 1. So hopefully you don't even need all of that explanation. Maybe you've basically memorized that the natural log of 1 is 0. So that explains why you don't actually see f at c, because f at c is equal to 0. So this really is f of x minus f at c, because it's minus 0. So we have now determined that this really is, this limit represents the derivative of f of x at an x value of c. So let's go ahead and use our derivative rules to evaluate this limit. So we have learned that if f of x is natural log x, then the derivative is 1 over x. And the derivative at 1 would be 1 over 1, which equals 1. So evaluating using our derivative rules is a lot easier than trying to evaluate the limit directly. We now know that f of x is equal to natural log x and c is equal to 1. So let's write a limit for f prime at 1 using the traditional definition of derivative. So that goes like this. The limit as h approaches 0 of f at c plus h minus f at c all over h. Well, function f is natural log x. So if I want to do f at c plus h, then I'm doing natural log, I'm doing natural log at c plus h. But we know that c is 1. So we're going to do natural log at 1 plus h. Then we do minus f at c. Well, f at c is natural log 1 because we're just taking 1 and plugging it in. So we're doing minus natural log 1. But as we just discussed a moment ago, natural log 1 is 0. So we don't really need to write anything at all right here. So it comes down to this. So the point is, if you were to see this limit on a test and it said evaluate, rather than actually trying to figure out how to evaluate the limit directly, you should recognize that this is just the derivative of the natural log x evaluated at a c value of 1. And the quickest way to evaluate that derivative is using your derivative rules. Last one, this is problem number 8. Once again, it looks like this might be the alternate definition of derivative. If it is, then this is x minus c, which would mean c is equal to 2. For the alternate definition of a limit, we have f of x minus f at c. But I only see one term here. So I'm kind of betting that this term is f of x. Let's play around with that for a minute. Let's assume for the sake of argument that f of x is the sine of x minus 2. If that's the case, then what would f at c be? So, okay, f at c would be sine of c minus 2. So that would be sine of 2 minus 2, since c is 2. But that would mean the sine of 0. And we know that sine of 0, okay, 0 is right here, sine is the y value, so sine of 0 is 0. So that would explain why there's only one term, because f at c is 0. So this does fit the pattern for the alternate definition of derivative, and this limit is really the derivative of f at 2, where function f is the sine of x minus 2. So rather than try to evaluate this limit directly, let's skip over here and use our derivative rules. We know that f prime will be the derivative of sine, which is cosine. So we have the cosine of x minus 2. Technically, we would now use the chain rule and multiply by the derivative of the inner function, but the derivative of x minus 2 is just 1, which doesn't really change the answer. So the derivative of the sine of x minus 2 is the cosine of x minus 2. But we are supposed to evaluate f prime at 2. So this would be the cosine of 2 minus 2. All right, but this is the cosine of 0. And again, if this is the unit circle, here is 0. Cosine is the x value, and the x value here is 1. So cosine of 0 is 1. So that is the final answer. So if you were given a limit like this and asked to evaluate, the quickest way to evaluate is to realize this is really the derivative of this function evaluated at 2, and use your derivative rules. So now that we know that f of x is the sine of x minus 2, let's go ahead and set up the derivative using the traditional definition of derivative. So here is the traditional definition of a limit right here. But we already know that c is 2, so let's replace these c's with 2's. So now we need to do f at 2 plus h. So that means we need to take 2 plus h and plug that in right here. So this is a little bit weird because it's going to be the sine of 2 plus h. All right, that's just the x part. But then we will still have this minus 2 on the end. So that's going to simplify down to the sine of h, because the 2's will cancel. So f at 2 plus h boils down to sine of h. So I will have sine of h minus f at 2. So now let's talk about what f at 2 is. So f at 2 means let's plug in 2 for x. So this would be the sine of 2 minus 2, which would be the sine of 0, and we've already discussed that this is equal to 0. So that means this would really be minus 0. So you could write it like this, or you could just not put the minus 0 at all. You might see it like this. So this limit is another way of writing the derivative of f at 2, where the function f is this function, sine of x minus 2. And that was problem number 8.